Let's look at another two-tailed hypothesis problem. And this is one I took from an old test. I went from and looked for some old final solutions, or some, I guess I should say, test 4 solutions that I've had, and I got some old problems. So here goes. And this is the way I express them in an in-person class. For number 1, state the hypotheses. The mean dexterity score has a mean of 30 and a standard deviation of 6 for everyday schmoes, right? A sample of 4 that's completing some kind of dexterity training, let's say, shows a mean of 35. Well, how about that? Right away, it appears to be the case that they've improved, although that wasn't specific to our hypothesis. We hypothesized that dexterity training affects dexterity. Now, when I say affects, that doesn't suggest improving or worsening. It just says affects, just like a two-tailed test would often reveal. What are the null and alternate hypotheses for a two-tailed test, alpha of 05? Now, please bear in mind that I'm trying to repeat the exact process by which we're expressing these hypotheses. The null hypothesis says the dexterity score among people who took the training. This is people that are the population of people, the hypothetical population that took this dexterity training, whatever the heck that is. This says it doesn't make any difference. It still equals 30. Dexterity training doesn't do squat, right? Now, conversely, what's the alternate? Well, in that case, dexterity scores among people who took the training are different than 30. Now, again, we're kind of holding our nose, and that might be suggesting that the dexterity training actually makes it worse. Now, again, in the real world, we wouldn't go there, but we're just going to kind of pretend here that this is a legitimate research hypothesis that just says it affects it. I'm not really sure what it'll do. Will it make it better or worse? So what I'll then do in step 2 is set the criteria for a decision. Now, what I've done here is I've already put the z obtained down there. Just try to ignore that, the green part. Just focus on the 1.96. Now, why did I use 1.96 again with 0.0250 here? 0.0250 here and 0.0250 on the other end. Well, it's alpha of 05, right? I said alpha of 05, which is pretty typical, two-tailed, okay? So I'm going to take that 0500 and divide it into 2 parts. And this is a capture from the tables. This is from the unit normal z tables. And I just took a capture of it. And sure enough, that's 0250 in the tail. And where did that come from? 0500 divided by 2. So again, you don't have to do any of that in your noggin. Just use a calculator if you want to figure out where that came from. So I put the goalposts up. There are those red goalposts that are exactly similar to problems that we've done before. And then here's the sample mean. I collect a sample of 4, just 4 people. That's not very many, is it? Completing dexterity training, and they show a mean of 35. Okay, good. And I want to calculate z based on that. Well, the first thing I have to do is I take the standard error from the problem, and I take the sample size and plug it in to stand for my standard error. And sure enough, 6 over radical 4 is 6 over 2 is 3. Okie doke. And then I plug that into z. So here's 3, and it's just 35 minus 30 over 3. 5 over 3 is 1.67. What is that? That's my z obtained. That's the obtained value of z. And where am I going to put that? Well, here's step 4. I put my obtained value of z here in green, and here's my critical values of z, the goalposts, if you will, here in red. Now, the question is, did it fall outside over here in these critical regions? It could have fallen in either of the 2 critical regions, and it did not. So what are we going to do? We're going to fail to reject the null hypothesis. We did not achieve statistical significance. Now, you might be a bit vexed here. Say, wait a minute. Gee whiz, it looks like it had an effect. It made it different by 5 points. You know what I mean? Gosh, why did we miss statistical significance? That's kind of annoying from the standpoint of the researcher. Well, among the things that may have caused it to miss is the fact that we only had a sample of 4. What are the implications of using only 4 people? Is that this number, radical 4, is kind of smallish, which makes this number kind of largish. The smaller my sample size, the bigger my standard error, and I've got to divide by a bigger number here, which had the effect of watering down the overall z-score. When we have a small sample size, that's something that's frankly a danger. And then I just didn't enjoy much of an effect here. Now, it's not the case that we cynically chase large samples specifically to get statistical significance, because as we'll speak of later, we're going to have to confess to an effect size anyway. There's a separate thing called an effect size that talks about the practical effect of what we're doing here. But nonetheless, in this problem, just going through the 4 steps, the hypotheses are precisely as the same we took before. I wrote this idiosyncratic phrase here, but it's something that you could do. The dexterity score among people who took the training. There's this hypothetical universe of people that took the dexterity training, and according to the null, it didn't make any difference. It should be equal to 30. That's going to stand as my null hypothesis. I set my, goalposts here, if you will. And if the obtained value of z doesn't exceed those goalposts, it doesn't fall outside, then I'd fail to reject the null hypothesis. Now, would the researcher prefer to reject it? Yes, they would prefer to reject it. But what we're literally saying here, and I'll wrap this up, is that in this problem, the probability of obtaining this sample mean, given that the null hypothesis is true, was not particularly unlikely. And given that that sample mean, assuming that the null hypothesis is true, was not particularly unlikely, I'm going to go ahead and not reject the null hypothesis. I'm going to fail to reject the null hypothesis.